So they say our oceans are missing a lot of plastic waste. This has been called the plastic waste paradox or something along those lines. And it states that the amount of plastic waste that we have estimated to go into the ocean is far greater than the amount of plastic waste that we estimate to be currently floating on top of the ocean. And this all ties into one of the areas that I think is actually understudied in the field of microplastics, let's say, is the relative rates of biodegradation, chemical degradation, and mechanical or physical degradation for plastics once they get out into nature. And that's why I picked this paper, because it starts to address that, and it does that in with respect to this so-called plastic waste paradox. So this is the paper, Plastic Photodegradation Under Simulated Marine Conditions. Here's sort of maybe the main problem statement of the paper. However, the observed inferred total amount of plastic marine debris at the ocean surface is seemingly more than one order of magnitude lower compared to the expected mass of positively buoyant plastic released to the ocean since the 1950s. Several explanations were brought forward to explain the missing plastic paradox. Okay, the missing plastic paradox. So we think that there's more plastic being released to the ocean than we see floating on the ocean. So what could possibly be going on here? One of the reasons this is such a mystery, at least in some people's minds, is because there's this popular misconception about what happens to plastic when it gets in nature. And that is that it all turns into micro and nanoplastics. Well, that's just not the case. This is one where the science is pretty clear, even though the scientists aren't always. But it's just an internet myth that's the final fate of all of the plastics, plastic waste that goes into nature. And so let's just take a look at this other paper. This has been out since 2020. So this is all about degradation rates of plastics in the environment. So, this isn't the first study to address this. This goes into detail about the different polymer types, what happens to them, what kinds of degradation mechanisms you get, what kinds of products you get. And so this isn't new. Like, I don't know exactly how this myth came about, that there's no chemical degradation for plastics once they get in nature, but the science has been pretty clear on this all along. So let's just take a look at some of the things that are said. As I mentioned, the science is clear. The scientists aren't necessarily clear about this. So here's some quotes just taken from introductions of scientific papers in this area. Once released into nature, plastics are susceptible to degradation, leading to the formation of microplastics, which is true, but it's an incomplete description of what happens. After being released into the environment, plastic products undergo a degradation process caused by the action of atmospheric agents such as waves, abrasion, UV radiation, and photooxidation in combination with biological processes, which leads to the formation of microplastics. So, like, all of that was great until the very end, which again is not completely false. You're going to get some microplastics out of these processes, but you're going to get a lot of other stuff as well. And I'll go through that in some detail in this video. And then one other quote: although the photodegradation process can proceed down to the molecular level, the degradation products remain polymers and may contribute to the dissolved organic carbon pool in the ocean. So you're getting a little closer to the truth here. Again, it's not wholly false. Some of the products from degradation are still polymers. It'd be hard to define them as plastics anymore, certainly. And some of the products are certainly not polymers, and they do contribute to the dissolved organic carbon pool in the ocean. We'll talk about that. Let's go through some news. So this is allegedly science-based news. Once the plastic is in the ocean, it decomposes very slowly, breaking into tiny pieces known as microplastics. Again, not false, but not a complete description of what happens. Research shows that plastic bags don't ever really decompose. Instead, they break down over a period of 20 to 1,000 years, releasing chemicals into our environment. Okay, 20 to 1,000 years. I mean, if you have a plastic bag that's buried in a landfill and there's no access to oxygen or heat, maybe it would take 1,000 years. Releasing chemicals into our environment, I guess that's true. There's no evidence that any of the chemicals are harmful, although it seems to kind of be implied here. But the research shows that plastic bags don't really decompose. That's just false. They do. Unlike some other kinds of waste, plastic doesn't decompose. There we go again. That means plastic can stick around indefinitely, wreaking havoc on marine ecosystems. Wreaking havoc on marine ecosystems is a bit much. There's some early evidence that very high doses will cause some problems with some fish. What's really wreaking havoc on marine ecosystems is overfishing, for example, and global warming, high carbon dioxide levels. Those things I would say are wreaking havoc. I would say maybe there's some preliminary evidence that there might be some concern about plastic causing some damage to marine ecosystems in some areas, in some situations. Social media, heat, sunlight, and other environmental stresses break down these plastics over time. Just like other materials, they get to the point where natural circumstances could no longer significantly break them down anymore. This is microplastics. So that was pretty good at the beginning, but here we have this myth that the size of plastics breaks down without any chemical changes, and it gets to some point, maybe microplastics, nanoplastics, and then they just stop. Like they just magically stop doing any more mechanical, physical degradation or chemical degradation, and they're just they're just there anymore. That they don't get to a point where, well, the point that natural circumstances can't break them down anymore is when they get to carbon dioxide. then that's pretty much done, and that then you're back in the normal carbon cycle. Plastic takes 1,000 years to degrade, never fully disappears. It breaks down into persistent, harmful microplastics. So I don't know what they mean by never fully disappears. Some microplastics are certainly too small to see by the naked eye, so you would think that means it disappears. But again, I think the point they're trying to make is they're not using the right words, but I think what they're trying to say is there's no chemical degradation, there's mechanical degradation to smaller sizes, and those micro nanoplastics hang around forever and do bad things. Here's one with some maybe more flowery language that really to drive the point home emotionally. It starts as a single plastic item exposed to sun waves and wind. It begins to break apart, becoming microplastics invisible to the naked eye. Plastic never disappears, it just gets smaller. I love the way they become invisible, but they never disappear. So I'm not exactly sure how that goes. But once again, I think you just have this general myth that a lot of people believe that there's no chemical degradation, there's only physical, mechanical degradation into smaller pieces, and those smaller pieces never get any smaller than whatever the smallest level is that you want to do the maximum damage to the environment. So that's just not true. And you've got all these words now. You've got degrade, photodegrade, decompose, disappear, break down, stick around, deteriorate, break apart, get smaller. All those things appearing in all of these statements. This sort of language is just not very specific. So I wish people would at least be a little bit more clear what they meant in terms of biodegrade, chemically degrade, physically degrade. So that's the way I'm going to talk about this. I hate to just be negative and just say, oh, you're doing it wrong, you're doing it wrong. So if I were to write an introduction to any of these papers about microplastics in nature, I think this is the way I would do it. I would say in nature, mechanical forces reduce plastic particle sizes as synergistic chemical reactions degrade polymer chains via scission and oxidation. Although the terminal products are CO2 and CO in aerobic conditions and or gaseous hydrocarbons, the intermediate macro, micro, and nanoplastics can persist for many years with potential for environmental and health impacts. So I'm not saying that micro and nanoplastics don't exist, and in fact they do, and they do hang around for years, and fish can eat them and we can eat them. So it's not that they don't exist, it's just that they're transient and they're on their way to some final product, which is going to be a gas that is going to go up into the atmosphere. Now, whether or not that's a good thing is kind of open for debate. Personally, I think microplastics are less harmful than CO2. I think a lot of people really want the problem to disappear from our sight, like they just don't want to see plastic. And so there's this thought that biodegradable plastics are great because they make the problem go away, when really what they do is they make the problem go into the sky. Like carbon doesn't suddenly turn into a void. If you biodegrade, all of these degradations eventually lead to CO2. It may go via CO, it may go via some hydrocarbon, but once it gets up into the atmosphere, it will slowly over time turn into carbon dioxide anyway. But nonetheless, I think you can write an introduction paragraph that is complete and informative and honest and still have it be part of a problem statement. Like you can still be concerned about micro and nanoplastics and be honest about the degradation mechanisms of plastic. Okay, let's start with biodegradation. There's readily biodegradable has a formal definition. It means you have to pass one of these tests. These are mostly variations on OECD 301. And basically what it involves is taking whatever material you want to test and exposing it to some aqueous mixture containing microbes from the local sewer, literally, that can eat it. And you look either for a degradation of the material that you're testing or an evolution of carbon dioxide indicative that the microbes have been eating it. No plastics pass this readily biodegradable test. Things like detergents and soaps generally will. I think almost all of them do. Most papers will pass this. I don't know about most. A lot of papers will pass this. If they have some sort of wax coating or something, they generally won't. Other material types won't, like glass, no way. The metals aren't going to pass it. So it's really just paper that's readily biodegradable. Now, there are also what I'm calling unready biodegradation. So things like PLA, polylactic acid, which is the most common biopolymer, will biodegrade, but it's not fast enough to pass the readily biodegradable test. Then there's some other things like hardwoods, oak and walnut even. They are not readily biodegradable. They'll float around for a long time. They will eventually biodegrade. Leather and then wax-coated papers a lot of times will be biodegradable, but not technically readily biodegradable. So let's talk a little bit about why some things are biodegradable and other things aren't. So let's think about some things that we know about. So what can we digest? And the microbes are better than we are at some things, but let's start with some things we know about and see if we can sort of detect a pattern here. So acetic acid is vinegar. We know we can digest that, right? It has a carbon to oxygen ratio of 1, 2 carbons, 2 oxygens. The energy there is 3.5 kilocalories per gram, and we metabolize that in less than an hour. So it's pretty fast. Then you look at something like sugar. Sucrose is a sugar. It also has a carbon-oxygen ratio around 1, similar amount of energy, and it takes us a little longer, maybe 2 to 3 hours to metabolize sugar. Then you get things that are more carbon and less oxygen. So linoleic acid, which is common in things like nuts, oils, and seeds. Now your carbon to oxygen ratio is 9. There's more energy in there. Okay, so it's over twice as much energy per gram, but it takes us about it takes us several years to digest that because it looks like a long hydrocarbon. Those oxygens are sort of where our body can do some chemistry. So our body's chemistry is not very good at processing hydrocarbons. They are tough to get a hold of, and that you kind of need some place to sort of start biting into it from the standpoint of our internal biochemistry. So having that carboxylic acid group at the end gives us a chance. We can start to biodegrade that, but it takes a really long time. There's a lot of energy there for us, but we're not very good at processing that because it's mostly hydrocarbon. Here's another fatty acid, lignoceric acid. That one is even more carbon to oxygen. That one's complicated, so it will become part of cell membranes. And we can digest that, as I understand it, over long periods of time. But we kind of have to break it down into smaller pieces before we do that. So that's a tough one, but our bodies can still do something with it. Then you get to nonacosane, which is naturally occurring. It's in olive oil. Cuticular waxes, which are the waxy coating that you find on most vegetables, I think all vegetables actually, and most plants. And it's also a major component of paraffin wax, which is paraffin wax is a normal food additive that goes into a lot of foods. So we get a fair bit of this coming in, but we can't digest it. So it just sort of sits in fat cells for a while, and then we eventually work it out of our body over a period of several years. And again, it's because it's all hydrocarbon, right? There's nothing there for our body to do any work on. There's no oxygens or other places to really grab a hold of this molecule and do something with it. So it just sits there for a while and we finally clear it out. And then there are polyethylene chains, which obviously is sort of the same thing. So our bodies don't know what to do with that. It's all hydrocarbon. There's no place to really start any chemistry. And so polyethylene, which is a type of plastic, it just sits there until we clear it out, which is usually pretty quickly. But there's a lot of energy in these hydrocarbons. It's just that our bodies are not adapted to do anything with it. So let's move on. There's mechanical and chemical degradation, and these are the operable modes of degradation for plastics, okay? So mechanical, you have impact, compression, attrition, shear, and fatigue, and I've just given you some examples. Impact would be like hit it with a hammer. Compression would be you just keep squeezing it, so you put it in a vise and you keep squeezing it until it starts to break. Attrition would be like rubbing sandpaper on it. Shear means you're cutting it like with a scissors or a knife. And particle fatigue would mean like if you had it in a dryer for a long time and it finally just you just keep hitting it with low energy for a long time and the particle eventually starts to wear down. Chemical degradation includes reactions with water and oxygen. I should say water or oxygen, and it's driven by sunlight or heat. And the sunlight-driven reactions are the ones that are a focus of the paper I'm going to go over eventually. Okay, before we go on, you may have noticed in my proposed introduction to microplastic research paper, I said synergistically, I said something about there's a synergism between chemical and mechanical degradation. I don't know how well established that is, but it's almost certainly true. I would say certainly true. If you think about the structure, like the material science of a plastic, of a polymer matrix, it's very different from what you may have learned in an introductory chemical class about, say, a lattice structure. So if you think about, well, most of the materials, so glass, aluminum, steel, not paper. Paper is more like a plastic in this regard. Um, but so glass and the metals, you can think of those like a bunch of blocks stacked together. Maybe put some Velcro on the outside of these blocks so that they hold together pretty well. And then think about making an enormous wall of these things. So there are trillions and trillions and trillions of these blocks held together in this wall. And then you just start bashing that wall and knocking things apart however you want to do it, or you shear it, you hit it with a huge sword or whatever. You start breaking it down. Well, all those cubes will still be cubes. It's just that pieces will break off, but they'll still be made out of those cubes, right? It'll just be smaller than the wall started off being. And so, ironically, this idea that that particles break down to smaller and smaller size without any chemical degradation is more or less true for glass, for silica. You do get, they're like siloxyls at the end. So instead of SiO-Si linkages, it'll be SiOH. So there's, let's just say, surface effects. But overall, the basic chemical composition of the tiny particles will be the same as the overall particle. There's no oxidation that happens because glass is already fully oxidized. It's silicon oxide. There's no higher oxidation state of silicon to go to. So that just breaks down. And really, this myth about just going to microparticles and nanoparticles very slowly is closer to true for glass. It will turn into smaller and smaller particles. The nanoparticles will eventually go to what's called silicic acid. So even they don't stop, but you're talking about thousands, maybe millions of years for this to happen. Plastic is very different. So sometimes people describe the material science of plastic using spaghetti. So you think a bunch of cooked spaghetti put together. I think that's a useful place to start because the aspect ratio is closer to correct than a cube for sure. That means the length to width ratio for a spaghetti noodle is a lot more representative of the molecular shape of a plastic molecule, of a polymer molecule. And I think a plate of boiled spaghetti also gets to the point that these that the polymer chains are sort of entangled, mixed together, interconnected. It's very difficult to separate them out one by one. I would take this analogy a step further and say not just like a nice plate of spaghetti that you might make, or you might have a nice restaurant where you could grab one individual noodle and slowly pull it out, or like Lady in the Tramp, I guess, like suck it out with your mouth. Think more about like 7th grade lunchroom spaghetti prepared by someone on minimum wage who really just doesn't care. So like spaghetti that's been boiled in a pot that's overfull. There's not enough water in there. They do nothing to remove the starches afterwards, so it's not sent through a colander and rinsed. So these spaghetti strands are really stuck together. Maybe they even have this big, massive, entangled mess where you couldn't possibly pull one apart from the other because they're stuck to each other just as much as they are stuck together as an individual noodle. I think that's closer to the way plastics are. And you think about their elasticity. Well, that's because if you pull them apart, it's not easy to pull any single chain out of there. So they're not brittle, right? They stretch, they elongate, and they tend to come back together. And it's because these spaghetti noodles are sticky. They stick together. Okay, so what does that mean in terms of chemical versus mechanical? Well, if you want to break apart this, and again, you have to put trillions and trillions of these noodles together to really understand this. So you have this wall of trillions of sticky noodles together, okay? Now you break that apart, it's not going to come off in these nice individual noodles, right? You're going to break some noodles. And what that is chain scission. Okay, so that means the polymer chains are coming apart. And when they do that, you generate highly reactive fragments of the chain that are susceptible to oxidation. Okay, so if you mechanically degrade a polymer, a plastic, you're going to get some chemistry. Now, exactly how much? Is it mostly on the surface? These are questions that really need to be answered. But for sure, you're going to get some oxidation along with that if there's oxygen around to do oxidation. Otherwise, you're just going to get chain scission. But for sure, you're going to get some chemistry. Now, it also works the other way. So the more chemistry you do, the more you're going to break up this this stickiness. These noodles sticking together, I guess as you do chemistry, maybe it's like adding some oil in. I don't know, maybe the analogy breaks down a little bit there. But what it comes down to is in a plastic, there are microcrystalline domains, so little regions where the chains are stuck together really tightly. They're so tight that they have some crystallinity to them. They look almost like a lattice compound because these chains are aligned so nicely. Now, they can't do that once you start to mess with the chemistry. Okay, so you start putting oxygenated moieties on the chains. They don't stack together like that anymore. So what happens then is the polymer structure, the plastic, loses some of its resilience, some of its ductility, and so it becomes a little easier to break. So these things are going to happen synergistically. You're going to get mechanical and chemical degradation. The relative rates are not really very well established, but I'm pretty sure that when you break something apart, you're going to start to see chemical degradation. And as you see photooxidation or other kinds of chemical degradation, you're going to lose the integrity of the piece of plastic and you're going to get faster mechanical degradation. And again, I think this is an area worth studying, and that's what drew me to this paper, where they're starting to talk about the rates of photodegradation, which is a type of chemical degradation under marine conditions. So that's the other nice thing about this, is they're really bringing it to real world conditions, or at least close to real world conditions, to answer some of these questions. So let's talk about how they do that. So the photodegradation experiment, they start with just a bottle. They add seawater, about half full with seawater. Then they add a disc of plastic. It could be polyethylene. HDPE is high density polyethylene. They also did some study with polypropylene that I'll talk about, and they looked at a couple other polymers. The reason they focused on polyethylene and polypropylene is because they float, as some other groups maybe need to learn. But polyethylene and polypropylene float on water, and so they are more susceptible to photodegradation. Photodegradation is much more important process for polyethylene and polypropylene, so that's where they focused. And then they put a butyl rubber stopper on the top, and that's going to come into play again later. So then they turn this upside down and shine UV radiation on it, which is something like 9 to 25 times the intensity that it will experience in the ocean. Now they turn it upside down because they don't want that stopper blocking the light. They want the light to get to the plastic and do its work. And when they do that, what happens is they start to make all these products, okay? So let's start at the top. So hydrocarbons, HC is going to mean hydrocarbons. That's things like methane and ethane. They make some carbon monoxide, which they measure. They make some carbon dioxide, which they measure, that carbon dioxide is in equilibrium with carbonic acid, right? Because CO2 dissolves in water and reacts with water to turn into carbonic acid, H2CO3, and then that, of course, will be in equilibrium with bicarbonate and proton. So they just put all that together. The carbon dioxide and the dissolved inorganic carbon get lumped together at the end. And it's essentially CO2 that's either in the aqueous phase or in the gas phase. Then there's dissolved organic carbon, and that's what I was talking about. Like, this is the fragments of spaghetti noodles that are coming off from your big plate of spaghetti. It's it's oxygenated hydrocarbon fragments that can dissolve in the carbon. I should also say dissolved is a little bit of a misnomer here. This is where the accounting for micro and nanoplastics would be as well. It's not all dissolved technically, but they treat it as dissolved organic carbon for accounting purposes. So I want to talk a little more about what dissolved organic carbon is. It's pretty complicated, and when I first started reading this, I got a little frustrated. I'm like, why don't you just say what it is? Well, the reason they don't just say what it is because it is a million things. Literally, well, I mean, maybe it's not quite a million, but it's thousands of things. Okay, so this is actually from a little different paper where the focus of this paper was more to characterize what the dissolved organic carbon is. But I wanted to show this to you. So this is a mass spec experiment. So the x-axis here is molecular weight. Yeah, so the black stuff that goes above the line is what was produced for them when they in the dark, so just sort of thermal treatment. And then the orange peaks below are what was produced when they used light treatment. So each of these lines is a different molecular species, okay? So you've got so many different things. It's hard to wrap your mind around what it is in terms of the chemical. This isn't surprising. You're starting with polymer chains that are tens of thousands, maybe a couple 100,000 molecular weight, and you're breaking them down with a variable degree of oxidation. So of course you're not going to get a nice clean molecular species out of this. So if you were to follow this all the way out to a higher molecular weight, that's where the polyethylene is. That's kind of where you start. If you go to even lower molecular weight, you go to carbon monoxide, carbon dioxide. So you kind of start with something on the right. You see all this stuff in the middle. You're eventually going to get down to the stuff on the left. So the molecular weight is decreasing, the oxygen to carbon ratio is increasing as you get this chemical degradation. This is a kind of a cool way to represent the distribution of products. So here, instead of molecular weight, they're looking at it in terms of atom ratios. So the x-axis is the ratio of oxygen to carbon. The y-axis is the ratio of hydrogen to carbon. And you can see, again, where you would start would be in the upper left in this case. That's where polyethylene would be, a hydrogen to carbon ratio of very close to 2. And then carbon monoxide would be at the bottom right, and carbon dioxide would be a little further even to the right. So again, you can kind of see this progression from plastic to gas. It goes through a gazillion different intermediates that have different amounts of oxygen to carbon and hydrogen to carbon ratios. Now, what's interesting about this is if you look at what we talked about that was digestible earlier, things like acetic acid, sucrose, this is roughly where they would fall on this chart, right? So when you start to get all this oxygen to carbon ratio a little higher, well, now you start to wonder, could this be digestible? Linoleic acid would be about there. Cellulose, which we know is, that's what paper is made out of. It's also what celery is made out of. It's a pretty common component in a lot of vegetables. We don't actually digest cellulose. We can't digest cellulose. No animals can digest cellulose. I went down a rabbit hole on cellulose. It's a microbe that lives inside of some animals that digest the cellulose for them. So we don't have this microbiota that does this for us. Some animals do. But apparently no animals actually have the enzyme that digests cellulose. Okay, just a little side note for you. So it turns out this is true. So I looked this up. There are a couple of papers that show this, that the dissolved organic carbon that comes away from these plastics is in fact um, eaten by microbes. Okay, that's established. This is one paper. There are a couple others. So while plastics aren't biodegradable per se, you get this mix of now chemical degradation and biodegradation. So if it's in a marine environment and you have this chemical degradation going on, that makes them digestible. And so there's some microbes around that are just kind of hanging out waiting to eat these up. And like I said, the ones with a lot of carbon in them have a lot of energy. So you'd think this is pretty tasty for a microbe that knows what to do with it. So this study did a great job with controls. So here we have some test containers, as I described earlier. We're going to shine a light on them and see what happens. Well, they also did some controls with no plastic in there. And that's how they account for what may be coming out of that stopper, for example, or any other thing that might be generated from the seawater, I guess. I mean, whatever you get in the absence of plastic, they're controlling for that by just doing one without plastic around. They also do dark controls, so they have it at the same temperature. They set it up exactly the same way, but they just don't shine a light on it. It's in the dark. And that way they can separate, or they can isolate the photodegradation kinetics from what would happen in the absence of light at the same temperature. 45 degrees was selected. It's pretty hot even for tropical regions in the ocean. So it's not ideal, but shining the light on the containers, on the vessels, caused the temperature to go up to 45. They had some cooling fans in there, but that was about the temperature that they could maintain. And so they just did their controls at the same temperature. They also measure in triplicate. So the analyte and the control are both done in triplicate, which is great. They get pretty good reproducibility. They just did one blank per experiment, so which is fine. And what they get is an evolution of products that looks something like this. So now you know what all of these abbreviations mean. The green is the dissolved organic carbon. That little black trace is hydrocarbons. That little yellow trace is carbon monoxide. And then the slightly larger blue trace is the carbon dioxide. This is what comes off from virgin polyethylene while they're doing their test. The x-axis is time, so it's some number of years. And then they treat this data, they just add all of this together and they say, okay, what percent? So if you look at the y-axis on the left, that's the percent of the original plastic disc that remains over time. And on the right, it's the milligrams of carbon per square centimeter of surface area that has been degraded over time. And then that time equivalent in the subtropical ocean on the x-axis, so they're correcting for the photo intensity that would be experienced by a subtropical ocean. So that is an expanded time frame there. They don't actually do the test for 0.12 years. I think they do them for about 5 days. And so that's how they correct for the photo intensity that would be experienced in the ocean, is they change their x-axis. So I mentioned they do this for polyethylene and polypropylene. I don't know that I mentioned they also do it, and I thought this was really a great touch for making this even more realistic. They use what they call ocean polyethylene. That's sample C, the second one from the left there. And ocean polyethylene means they actually went to the ocean, found some plastic floating there, and took a piece of that, tried to cut out about the same size and dimensions as their virgin polyethylene, and did the same experiment with that. Okay? Then they do the exact same thing with virgin polypropylene and ocean polypropylene, and look at the kinetics of carbon evolution from these plastics over time with the light shining on them. All of these data are corrected for the control experiment with no plastic and also corrected for the dark experiment with no light. There's some very interesting differences here. For example, you see the polypropylene for both the virgin and the ocean are degrading much faster than the polyethylene. And the other thing you see is, well, let's start with the one on the far right, the ocean polypropylene one. You see this very strange turnover where the evolved products sort of come to a maximum and then they start to go back down. So this is totally unexpected. And what they did, which is reasonable, is they said, look, we can fit a line to 3 of the 4 of these and it makes sense. And really those lines look okay. But trying to fit a line to that 4th one, the ocean polypropylene, it just doesn't work. It doesn't look like a line, so we're just not going to fit that and we're not going to report any data for that. So that's fair. But you know, I also looked at the ocean polyethylene one really closely, and it looks to me too like maybe it sort of goes to a maximum and then levels off. So I think the ocean polyethylene and the ocean polypropylene both have some strange kinetic behavior that I was wondering if maybe we could come up with an explanation for. So let's start with the polypropylene one because that's the one where the effect is most pronounced, and you know, the evolution is a little faster, so you get a little better signal noise. So the first thing I thought was, well, there's no way this is doubling over, right? You're not going to have material disintegrate into nothingness, right? So there isn't really a very good explanation for this, other than maybe it's because when you correct for the dark control that doesn't have light shining on it, maybe that is subtracting out more than we want. And the authors thought about that too, and they were kind enough in the supplemental material to give us a kinetic profile for the one with no dark control. So this is the one on the right is the same as the one on the middle, except they haven't subtracted out the product mixture that has come out from the dark controls over the course of time. Now, this has a shape that is a little easier to understand, and this looks to me like approaching an equilibrium. Like it's coming to a dynamic equilibrium where initially the concentrations are increasing significantly, but here towards the end of the experiment, those concentrations are remaining more or less steady. And I thought, well, what could be going on here? So the first thing I thought was maybe the CO2 is escaping. You've got some gases in there. Maybe they're sneaking out. And so what you have is you've got this CO2 being generated, but it's also being released. And so it comes to this dynamic equilibrium. And my first thought was, well, the way they analyze this is they jam a syringe needle through the septum at the top to get some gas. That's the first thing they do. And I thought, well, now you have a hole in there and the CO2 is escaping. But not so fast, because when they do that, they're done. Okay, so they started a whole bunch of these at the same time. And once they pull one out and do the analysis, they're done with that one. So these are all from identical triplicate experiments that they've stopped at different times. So it's not some, needle hole that's allowing gas to escape. The next thing I thought about, how could CO2 be sneaking out? Well, and I remembered that the stopper they used was butyl rubber. And one of the things I remember from a safety meeting from a long time ago is talking about how hydrocarbons can diffuse through butyl rubber. We use butyl rubber for the gloves in our glove box. So when we would do work under inert atmosphere, you literally have a big box where you're doing your chemistry. You have these big plastic gloves that you put your arms in. So your arms are inside the box, but you're not exposed to what's going on in there. However, hydrocarbons can diffuse right through the butyl rubber. And we adopted some new procedures and policies based on this. But I thought, well, if hydrocarbons can get through, maybe CO2 can as well. So if that's happening, then how do you get to an equilibrium? Well, I thought, well, maybe the dissolved organic content also turns into CO2. That CO2 is escaping the container, and that's how you come to a sort of dynamic equilibrium. There was some information on this in the literature. I didn't find a great scientific paper, but I did find this, which basically says diffusion of CO2 through butyl rubber is slow, but the solubility of CO2 in butyl rubber is high. So there is a relatively fast transport of CO2 through butyl rubber. And there was some discussion about bike riders. If they get a flat, they fix the flat, they would have these air cartridges, but it wasn't air in them, it was CO2. So they would fill up their repaired inner tubes with CO2, they'd ride it home, and the next day, without fail, it would be flat again. And so that's how this discussion online came about, is these cyclists asking, why does my tire go flat? And the reason was because CO2 slowly diffuses through the butyl rubber and escapes, and that's why it goes flat. It'll get you home, but then you got to put air in it again, which will not diffuse through, at least not as fast. So I looked at this kinetic model. I had to take that data and extract it. They didn't provide me a table, unfortunately. So I used something called WebPlot Digitizer. You basically take a picture of what you see, and then you come in here and you can move these little dots around, and it will return X, Y coordinates of what you want. You can see, like, I had to figure out where the time points were, and I had to move these things pretty carefully to be able to measure these. Having a table of data would have been a lot nicer, but I think there's still pretty good approximations. So once I had all that data extracted, I was able to plot that in Excel. So the dissolved organic content, millimoles carbon is on the left. That allows you to look at everything on the same axis. So dissolved organic content comes up and then levels off. The dissolved inorganic content plus CO2, so that's basically CO2 in the gas and aqueous phases put together, also comes up and levels off. And then the CO and hydrocarbons just kind of come up slowly. But the error in those measurements, especially after my extraction process, is relatively high. It turns out this kinetic model fits really well to these data. As you can see, I mean, you've got the lines going more or less right through all the data. And the kinetic rate constants that got me there are here. As you can see, this rate constants for CO2 escape is quite high. But the interesting thing here that really made me think about what I was doing, this rate 1, the rate of polypropylene turning into carbon dioxide, the best fit was for that rate constant to be 0, or that rate to be 0, I should say. So what this fit is telling us, if everything is correct, is that you're not making carbon dioxide directly from polypropylene. It's all going via the dissolved organic content. And I thought that was, if that holds up to further experimentation, I think that's an interesting learning that could help to further understanding of these degradation mechanisms. That made me think a little bit further. Do I really have the right model here? Yes, the fit is great, but am I getting it right? And I thought, well, it's probably relatively unlikely that any of these small molecules are going to come directly from the polypropylene. Probably they all come from the dissolved organic carbon. And so I moved to this model where You just have one rate going from the polypropylene to the dissolved organic carbon, and then that splits off to these three different gaseous products, and then I still have CO2 escaping the vessel. And I fit that, and the fit is just as good. I mean, it should be. I mean, it's basically the same fit as before with that rate constant for polypropylene going to CO2 set at 0. I don't think that you can say anything about the hydrocarbons and the CO, where they come from based on this, but just it seemed more intuitive to me that if the CO2 is coming from the dissolved organic carbon, these other products probably are as well. And so this is the model I stuck with. The rates here now, that rate of polypropylene going to dissolved organic carbon, that's the degradation rate. Okay, so that should compare to, in theory, it would compare to the linear fits that are already in the paper. Now this was for light plus heat. So we haven't corrected for the degradation, the thermal degradation due to just heat yet. And the way you have to do that is I had to take their uncorrected plot minus their corrected plot to back out what the degradation pattern must have looked like for their control experiments. And so that's what I've done here. And you can fit that, and it fits the same model as well. So here we have a rate constant for thermal, for heat only. The previous one was for light plus heat, and you can just subtract this one from the previous one, and that's your rate constant for light. And I'll do that at the end. I want to quickly go through and show you, I also did this for the virgin polypropylene, so this is not the ocean polypropylene. So this was the nice, clean sample that hadn't been in the ocean at all. Interestingly here, the rate constant for CO2 escape is 0. And this is one where they fit that line and they got a pretty good fit. And if there's no CO2 escaping from the vessel, then you would expect that linear fit to be pretty good. So this is all consistent. It does raise the question of why CO2 is escaping from the previous one and not from this one. I think it's because if you back out the total amount of CO2 that's generated from the ocean polypropylene one compared to this one, it's a lot more. It's like 10 times as much. I suspect it might have something to do with overcoming the natural buffer that's in seawater. Seawater has some boronic acid and some sodium bicarbonate in it, so there's a little bit of a buffer in there. And I'm thinking maybe the CO2 only starts to escape once it's generated enough acidity in the water to overcome that buffer. And then you start to get this partitioning out of the water into the stopper. That's the best guess I've got. It could be something else. I mean, I haven't proven that the CO2 is escaping the vessel in the previous one. This is some evidence that calls that into question. But that fit was pretty good, and it seems to match with theory. So I tend to think that's what's going on, but I'd certainly be open for other explanations. So I'm going to flash through these pretty quickly. You can do the same thing for the ocean polyethylene. This is both light plus heat. This is in the dark, so this is the control experiment for the ocean polyethylene. And then I also did a fit for the virgin polyethylene, corrected for the dark. And this one also has a CO2 escape rate constant of 0. So you would expect a good linear fit. Now you put this all together. So virgin polypropylene 50, the ocean 327. So it really speeds up a lot when it's been in the ocean for a while. Interestingly, polyethylene not so much. So 26 to 24. So it's about the same. You compare this to what they reported, and this is where I got a little sad because you can't compare to what they reported, and I'll go over that in the next slide. So what they report is 1.4 for virgin. They did not calculate for ocean polypropylene because of the nonlinearity, which is fair. 0.66 for virgin polyethylene and 0.63 for ocean polyethylene. In all cases, it's about a factor of 40 different. I can't figure out why. I can't come up with even some reasonable suggestion for why. The numbers on the bottom, their numbers in the report, I really suspect those are the right ones. Uh, they're pretty consistent with what I've seen in some other reports, and they also just make more sense in terms of the percent of the original plastic article that are degraded over the course of the experiment. Like the ocean polypropylene, you would have seen this, I think, by the time it was done. It would have had a massive degradation, and you probably would have figured out that your numbers weren't right. So what's going on here? Well, unfortunately, the axes on the bottom and the axis on the top don't seem to be presenting the same information. I have to work from the data on the top because that's the one that breaks the composition of the degradation products out into different types. So for me to do the fit that includes a CO2 escape, I have to know what the relative amounts of everything are. So I have to work from the top, but the top doesn't correspond to the bottom unless I'm totally missing something. So even if you just look at a single point, this one's about 0.2 millimoles. So if you just take that 0.2 millimoles and do some unit conversion, times 12 milligrams per millimole for carbon, and then divide by the surface area that they report, which is 0.75, you come up with 3.2 milligrams per carbon. But on the bottom down here on the right axis, it's about 0.9. So the top doesn't seem to correspond to the bottom. I think the bottom is right. I don't have even a clue why the top doesn't work. I don't think I'm doing something wrong here, so I'm not sure what's going on. But I think the trends that I saw in my treatment probably are still valid, but I don't really want to say much about the numbers. And I really wish the authors, I did ask them what's going on here, and I did receive some responses from them. They don't think CO2 is escaping from the vessels based on some control experiments that they did. I tried to push them a little harder on how relevant those control experiments were to the actual conditions for the ocean polypropylene degradation experiments, and I don't know, maybe they got tired of me, but there are a couple outstanding questions I have from this paper that could have made it a great paper, but I still think there's a lot to learn here. So in summary, this missing plastic paradox is not any sort of a mystery at all. It's probably just solar degradation and producing dissolved organic carbon that probably gets eaten by microbes nearby, or maybe eventually turns into carbon dioxide and some other things that go into the atmosphere. So it really shouldn't be surprising that the amount of plastic waste going into the ocean is not the same as the amount floating on the ocean. Polypropylene degrades faster than polyethylene. That seemed to be true for both the ocean and the virgin polymers, and under very well-controlled conditions and under less well-controlled conditions, that seemed to be the case. I would say there's some evidence from my treatment, but also just from sort of eyeballing the data. If you look at the initial rates for the ocean polypropylene, it's faster than the virgin polypropylene. So it sure looks like there's going to be some acceleration for polypropylene photodegradation as it ages. Obviously, there are a lot of follow-up experiments that could be done for that, but there's some preliminary evidence, at least, that that's happening. The other thing that I think is interesting is this CO2 appears to be generated via the dissolved organic carbon, not directly from the polypropylene article itself. And that has some implications for, what does that mean in a vessel the size of the ocean as opposed to about 100 milliliters, which they were doing. So the dissolved organic carbon starts to disseminate away. How fast is that relative to microbes eating it, for example? I think just a more sophisticated understanding of the degradation pathways just can lead to a better understanding of influences on marine life. The only final comments are, Improved vessel design could enable more detailed and reliable kinetic analyses. I would definitely look into this possibility, again, that the CO2 could be escaping. It would make the analysis a lot simpler if it wasn't. And it may be as simple as just performing duplicate experiments, one with a butyl rubber stopper and one with, say, a Teflon stopper, and just see if you get identical results or you see a lot more CO2 in the vessel with the Teflon stopper. Again, my treatment didn't prove anything, but it does seem to be a reasonable explanation for the behavior observed in the article. And then the final comment is, man, I would be a lot more greedy about how I treated this data. They just basically fit a line to the sum total of the carbon that was generated. And I think there's a lot of additional information from doing a more detailed kinetic analysis that involves all of the associated carbonaceous products that come out from the degradation experiments. So I think, I'm hoping somebody follows up, either this group or somebody else follows up and does more experiments like this. I think answers to these questions, maybe more reliable kinetic data, more sophisticated degradation models that account for changes in surface area as particles get smaller, for example. Take into account any degradation acceleration that may happen as the surface becomes more oxidized, or as I mentioned, like the physical integrity of the article starts to weaken with the degradation. So you could see all kinds of secondary effects if you do some more detailed analysis, some more experiments, some more sophisticated kinetic analysis. I just think there's a lot of information, a lot of additional information that could come from this type of experimentation. I think this paper is a great first foray into this. I really applaud their efforts at getting realistic data under as realistic condition as you could. I kind of feel like they got maybe 95 to 98% of the way to a beautiful protocol that maybe just a little additional work could get that all the way to 100%. But I really enjoyed reading this. It taught me something. That's always my litmus test for whether I want to read something is, does it teach me something? And this one definitely did. It's worth a read if you have the time. If not, I'll keep reading a few things for you and reporting them to you. So thanks for watching. There's more to come.